SwayamPrabha. Digital India. Educated India.
Hello, in this lecture I am going to discuss systems with mass flow. Till now what we were discussing was Newton's second law for particles with fixed mass, constant mass. Here we are going to look at systems where the mass might be changing or there is mass flow, there is mass flow through the system, and how the equations of motion are changed because of this mass flow, or how new terms arise in the equation of motion when you have either change in mass or mass flow. Therefore, we will start by deriving the governing equation of motion of systems with mass flow and look at examples. There are various instances or systems where you will find mass flow. For example, systems with steady mass flow. The first example I have written is the jet engine. If you consider an engine, a jet engine, it takes in air, mixes fuel, and there is combustion, and the gases, hot gases are ejected at very high speed in the rearwards direction, and that generates thrust. Now, at steady state, this flow of mass and the flow of fuel, etc., these are steady. So, these are constants, the rates, flow rates are constant, and that represents a steady mass flow. But when you consider this engine to be a part of an aircraft, let us say a fighter aircraft or jet aircraft, then the aircraft is supplying the fuel, therefore, the aircraft is losing mass, and we are going to see this problem for a jet aircraft which is moving and burning fuel at a certain rate. So, and then it becomes a variable mass problem. Okay. Then water jet ski, nowadays these amusement parks have water jet skis in which takes in water from the front inlet and it ejects that water at very high velocity from the rearward at the rearward nozzle in the rearward direction, and that propels the jet ski. Turbine, once again hot gases move through the turbine, and that is an example of a steady mass flow. It generates the force or the torque which drives the turbine. Systems with variable mass, the first example that should come to mind is a rocket. It does not take in air or something, it carries its own fuel, it carries oxygen, everything it carries, and it just ejects that. There is combustion and there is ejection. So, mass is ejected, and that becomes a variable mass system. Then motion of chains, this we are going to look at with examples, how chains can be variable systems with variable mass. Now, to derive the equation of motion of a system with variable mass, let us start with this figure where I have shown in gray shaded region, this is the system, this is our system. At this instant at time t, as indicated here, at time t, it has a mass m, an absolute velocity v, and some non-impulsive forces are acting. The net force acting on this system is F. These are non-impulsive forces and non-flow forces. As we move from t to t plus delta t, there is one more thing here. There is a little blob of mass indicated by delta m I. which is moving with absolute velocity u I, which is shown, and this blob of mass in this time t to t plus delta t attaches itself to the system, it enters the system, and from as the whole thing moves from t to t plus delta t, the system takes in this mass delta m I and ejects a mass delta m O at an absolute velocity u O. These things are all indicated here. It ejects a mass delta m O, little mass delta m O, and the ejection velocity is such that the absolute velocity u O is the absolute velocity of the mass thrown out of the system. And therefore, by mass conservation I must have the mass of the system after all these things have taken place in time t to t plus delta t. The initial mass was m, it took in this delta m I mass, this one, and it ejected this delta m O. Therefore, m plus delta m I minus delta m O is the current mass of the system after all these processes have taken place in time t to t plus delta t. And once all these things have happened, the system now is travelling at a velocity v plus delta v. Therefore, it has changed its velocity from v to v plus delta v because of these ingestion and throwing out of this mass. Let us recapitulate what we have discussed is u I, u O and v, these are absolute velocities. This you have to remember. U I was the velocity, absolute velocity of the mass that was ingested. So, just before its ingestion by the system, its absolute velocity was u I. Similarly, u O is the absolute velocity of the mass that is ejected out of the system, is the absolute velocity of the mass which is ejected out of the system. I can always find out the relative velocity by taking the difference with the velocity of the system. F is the net force, non-impulsive forces which are acting on the system, and these forces do not account for this flow forces. Flow forces we will see how they evolve. Now, we will write Newton's second law for this system. In this case, it is very simply written as limit as delta t goes to 0, change of linear momentum divided by change of time is equal to force. This is rate of change of linear momentum is equal to force. This is the form of Newton's second law. Therefore, we start with limit delta t tends to 0 1 over delta t. Now, I have to write in brackets what is change in linear momentum of the whole system. Now, change in momentum is final linear momentum minus initial linear momentum. What is final linear momentum? Final mass of the system times velocity of the system plus final this mass ejected times its absolute velocity, that constitutes the net final momentum of the system. This is the net final momentum of the system. We have the system itself and that ejected mass, both of them will together constitute the final momentum of the whole system. And what is the initial momentum? The system was moving, system of mass m was moving with velocity v, and there was a blob of mass delta m I moving with absolute velocity u I, and that must be equal to the net force acting on the system. If I do algebraic simplification, drop out the second order terms. What are second order terms? For example, the product of this and this will be second order because delta t goes to 0. Therefore, these second order terms can be neglected, If I do all these things, algebraic manipulations and simplifications, I will finally arrive at this equation, and you should be able to derive this. You should try and derive this expression. Of course, we have ignored the second order small quantities, and what definitions we have used? This you see is the relative velocity at the inlet. At the inlet of the system, u I minus v is the velocity of this delta m I with respect to the system. At the exit of the system, u O minus v is the relative velocity of delta m O at the exit with respect to the system. So, relative velocity with of inlet or incoming mass or outgoing mass, relative velocity of the incoming mass and the outgoing mass are represented by u I minus v and u O minus v respectively. And we have used these definitions. dv dt is acceleration A, which I have used here. mi dot is dmi dt and mo dot is dmo dt. Therefore, finally, this is our master equation, and this is the equation governing systems with mass flow. Now, we will specialize this to steady mass flow and variable mass flow problems in a moment. Let us try to rearrange this equation. What I have done is I have taken the additional terms on the left hand side to the right hand side, and this I call the forces because of the inflow and outflow. The force vector F is non-impulsive forces, external forces which are applied on the system. These are non-flow forces, but because of the flow, this incoming mass and outgoing mass etc., because of the flow, we have this force on the system because of inflow and force because of the outgoing mass. So, because of the outflow, this is the second term with that negative sign, it is the force acting on the system. Therefore, these two terms are now to be interpreted as force because of inflow and force because of outflow, and the total sum of these two is the flow because force because of mass flow. So, sum total of these two forces is the net force because of the flow, because of mass flow, and in certain situations we need to calculate the moment about certain points. For example, a vane is held fixed, what is the moment acting on the vane because of the flow. So, these kinds of problems we need to also calculate the moment. Let us say we want to calculate the moment about a certain fixed point O, which I have drawn in this figure, and I have marked the force because of inflow. These vectors are forces because of inflow and outflow, and you will note that the sign is taken care of. Therefore, the moment about O because of all these forces, because of the flow forces, is R I. This R I is the moment arm, R I cross the force because of inflow minus R O. This minus comes because there is this minus sitting here, minus R O cross, this is the force because of outflow. So, with this negative is a part of that force. Now, let us once again look at this expression and look at mass balance or mass conservation. The rate of change of mass of the system must be equal to m I dot minus m O dot. The m dot must be equal to m I dot minus m O dot. So, whatever is coming in minus whatever is going out. In steady mass flow problems, whatever is coming in must also go out. Therefore, the system mass is not changing. Therefore, m I dot must be equal to m O dot, and m dot is therefore 0. In variable mass problems, we have this these two are not equal, that is m I dot is not equal to m O dot. For example, in a rocket there is no inflow, there is only outflow. Therefore, the rocket must lose mass. We will also look at chain problems with which gains mass. Okay. So, we can specialize our master equation for both steady mass flow and variable mass flow problems, and here we are going to look at an example. This problem is sourced from the book of Merriam and Craig. A 250 gram ball is supported by the vertical stream of fresh water which issues from a 12 millimeter diameter nozzle with a velocity of 10 meter per second. Calculate the height h of the ball above the nozzle. Assume that the stream remains intact and there is no energy lost in the jet stream. These kinds of systems you might have seen in amusement parks. This ball, because of the water flow, remains suspended at a particular height. What is happening? The water particles are going and hitting and transferring momentum to the ball, and because of flow, just now we have analyzed, because of mass coming in and hitting it, there is a definite force. We have calculated this force, and that is what we are going to do. We will consider our system as this ball and a little bit its surroundings, so that we allow this water to come and enter our system. The first thing that we must do is fix up the coordinate system and draw the free body diagram. The coordinate system is very simple in this case. I have considered only the y coordinate direction vertically upwards. I have marked the velocity coming out of the nozzle and the diameter of the nozzle. We have to calculate the height at which the ball will stabilize. The free body diagram of the ball has been shown. The weight acts and the thrust because of the water. T represents the thrust because of the water stream. The equation of motion we have just now derived. The master equation, I have written out the master equation, and then I have struck off the terms which are 0, mass times acceleration. Now, the system is the ball is not accelerating, it is held steady. Therefore, acceleration of the ball is 0, therefore, the first term drops out. In the second term, the velocity of the ball, velocity v is the velocity of the system, which is our ball, which is 0. Therefore, that v drops out. In the third term, there is no the outflow velocity. What we are assuming is that water particles are coming, hitting the ball, and because it is hitting the ball, it is stopping there. The water particles come to a stop, come to rest. Therefore, the outgoing velocity of the water particles UO is 0. The absolute outgoing velocity of the water particles is 0, and velocity of the ball is already 0. So, therefore, the third term completely drops out from the left hand side of our master equation. On the right hand side, what we have is the force, the net force, non-flow forces. So, the weight is the only force that is acting, not related to the flow, and it is in the minus j cap direction. You should note that I have taken that y vertically upwards as positive. Now, just to recapitulate, this flow force, net flow force is minus T on the left hand side, and that acts in the j cap direction. Okay. Now, what we have to find out is the incoming, in this master equation, the terms remaining here, this term u I, this is what we have to calculate. What is this velocity? This is the absolute velocity with which the water particles are hitting the ball or coming into the control volume of the ball, our system. Therefore, I should first calculate the velocity of water particles at any height h, at any height h. And how do I do that? I consider that the water is moving freely in a uniform gravitational field. Therefore, the final velocity, this is the final velocity with which it hits the system, it enters the system. There is the final velocity square minus initial velocity square, which is the velocity at the nozzle. Final velocity square minus initial velocity square must be equal to minus 2 g h. Remember, our upward direction is positive, therefore, G, which is vertically downwards, induces that sign. And from here I can calculate with what velocity it is entering our control volume, our system. It is ui is under root of u square minus 2 g h, under root, whole thing is under root. And if you do a calculation, if you plug in the values, the velocity at the nozzle is 10 meter per second, therefore, that is 100 minus 2 times 9.81 times h is the height at which I am measuring the velocity. The other thing that I need to calculate in my master equation is mi dot. Mi dot is the rate at which this water is coming in into our system. It must be rho times area of cross section through which the water is coming in, rho times A times u, because no water is lost anywhere in between. All that goes from here, from the nozzle, must reach here. There is no loss in between. Therefore, the mass flow rate here and the mass flow rate here must be the same. Here I do not know the area. Remember that this nozzle is, this jet of water is going to flare up. The diameter here is going to increase. This is going to flare up because the velocity is reducing, and it must carry the same mass of water. Mass flow rate must remain the same. There is no loss. Therefore, since the velocity goes down, so area must go up, so that m dot at any level is the same. Therefore, I calculate mi dot from the mi dot at the nozzle. You can plug in the values at the nozzle. The diameter is specified, the velocity at the nozzle is specified, therefore, I can find out area, and hence I can find out mi dot. Now, from the equation of motion, now I will plug in all these values in the equation of motion, and I have a simplified equation, because I have this mi dot as rho a u, which I have written here. The negative sign comes from our master equation, times ui is this magnitude ui times j cap is equal to minus mg j cap. And if you plug in the values and do this calculation, which is straightforward, height comes to 4.86 meter. That means, this ball will remain suspended in steady state expectedly at 4.86 meter. Now, I am going to show this as an experiment. Here I have a straw, and here I have a little ball, and I have placed it on the straw, and I am now going to blow this and show you how this ball gets suspended. You can see that the ball hovers. That is because my rate of blowing is not uniform, and there is lot of disturbance because of the non-uniformity in the sphericity of the ball and the flow of air through the straw. If you can make this ball more spherical, this is quite a bit different from spherical, though it looks from afar like a sphere, but there is lot of perturbation from the spherical shape, and the flow from this nozzle is also little non-uniform. My breathing is non-uniform, and then there is vortex shedding behind the ball. After the air goes out, there is vortex shedding here, and that disturbs the ball, it oscillates. Therefore, you can do these experiments and you can verify or convince yourself how this suspension works with air, with an air stream or you can also do it with water. Let me just summarize. We have looked at the governing equations of mass flow systems, and we have looked at an example of a variable of a system under steady air flow or in water flow. Our example was with water. So, with that I will close this lecture.